Hello, we are Operation Omega, and we're working with Vanderland, an industry leader in creating logistic process automation via shuttle and conveyor systems. As Vanderland installs such large transport systems, their process for verifying the structure, components, and throughput can take a long time to complete manually. The process can be accelerated by identifying problems more quickly and reliably. For an example of an installation problem that needs to be detected, consider the racking support profiles. One system can have over 100,000 supports, which may be incorrectly assembled up to 1% of the time. This is one problem that needs to be detected in order to speed up Vanderland's verification. For this reason, Vanderland desires a more powerful tool, specifically a diagnostic robot, which can move through their structures and assist in quality assurance, ultimately reducing verification time. This robot solution must be able to traverse Vanderland's traditional conveyor surfaces and normal transitions, while being robust enough to withstand the vibrations induced by the system. The bot must communicate with Vanderland operators to provide sufficient diagnostic data, including visuals, audio, position, and appropriate sensors.
To begin design concept ideation, the team first created a function tree to identify the critical functions the Diabot must perform. These functions were broken down into two main functions, being mechanical and electrical. On the mechanical side, two main subfunctions were implemented: the ability to act as a transporter with its subfunctions shown, and the ability to protect the internal components. On the electrical side, the four main subfunctions were data collection, data analysis, signal connection, and the ability to control the mechanical functions.
The design process for the mechanical components began by determining the drivetrains for the Diabot. The two main considerations were continuous track and wheels. The decision was made in favor of continuous track due to the advantage when moving over rough terrain. Next, a symmetric design with a suspension system was chosen, as our sponsor, Vanderland, desired for the Diabot to be as versatile as possible. The suspension system works by having a suspension bar rotate around a fixed axle, with one end of the bar attached to the idle pulley while the other end is attached to the spring shock. As a force is applied to the pulley, the suspension bar rotates around the fixed axle and the spring shock dampens the force. For the drivetrain, a self-tracking tread was used that meshes with the pulleys. This prevents the tread from sliding off the pulleys as the Diabot turns. Overall, the biggest challenge for the chassis wasn't the technical design, but sourcing and integrating cheap components so that the Diabot remained under budget.
The Diabot uses a dual motor design in order to individually drive each side of the tank treads. The motors are set up in a 1-to-1 gear ratio to the axles of the driving sprockets rather than axial connections to avoid interferences between the motors. Given the diameter of the driving sprocket, the motors provide adequate torque and RPM to drive a Diabot of up to 40 pounds at a speed of roughly 2 meters per second.
For the modular attachment assembly, we went with a backless and vented body. This was to prevent any effects of a possible Faraday's cage, as well as vent the heat from the electrical components inside. We went with simplicity as being king for the attachment system, with a just 90-degree turn latch for locking the body, as well as drawer slides, as we saw this as the most user-intensive part of our build.
Here we have the entire electrical layout. A few main pieces of note include the 18-volt Milwaukee battery, which was chosen because it was easily accessible on the client site. Additionally, the Raspberry Pi was chosen as a microcontroller for the entire system because it can, in real time, collect data from the accelerometer, microphone, camera, and control the motors and LED while sending data out through its own Wi-Fi module in real time.
The Diabot software and user interface needs to support a few key features for operator feasibility. These are the movement and camera controls, live data processing and streaming, and alerting operators whenever data anomalies are detected. This software, electrical design, and mechanical prototype provide a proper Diabot concept validation. Our physical Diabot fits within the size constraints, can navigate through conveyor systems, provides removable treads for ride-along mode, and is robust against system vibrations. Finally, what's the point? Well, the Diabot and the accompanying software can be used by Vanderland operators to collect visuals and data within their large systems. Errors can be identified and therefore fixed much more quickly, which reduces system installation time.